So now we have talked about the GPS signal and the information that's being carried by that signal, those codes. So we have the carrier wave that's carrying a code. And now we need to talk about how is that used to determine the distance from us to the satellite. And what we're doing is we're going to use that GPS signal transit time. So the transit time of the GPS signal is what we use to determine the distance. So very similar to when you see a flash of lightning, our eye determines the start time. So that the flash of lightning travels to us at the speed of light. So we basically see it as soon as it happens. But the sound takes a while to get to us. So if we start our stopwatch when we see the lightning and we stop it when we hear the sound, then we know the travel time of the sound wave from the lightning strike to us. So that gives us the travel time here. And if we multiply that travel time times the speed of sound, we can get the distance from us to the lightning strike. So similarly, that's what we do with the GPS signal to determine the distance from us to the satellite. So the GPS satellite, or in this case they're showing it as a radio tower, right? It's going to transmit the signal to us. If we know when that signal was transmitted, and we can measure the time delay or the travel time from when that signal was transmitted to when it gets to us. And we can use, here's our travel time, delta tau, times the speed of light, c is the speed of light, and that's going to give us our distance. So the satellite and the receiver, you could think of it as if they're generating the code at the same time. But it takes a while for the code to make it to the receiver. The receiver knows when the code was generated, so it can measure this lag, time lag, or the travel time of the signal. And so our distance to the satellite is equal to the speed of light times the time lag. And that should not be a minus sign. That's a bullet point. So don't think of that as a minus. So our distance to our satellite is the speed of light times the time lag. So if we measure that delay, and we assume that the satellite signal travels at the speed of light, which we'll find out later that that's not a perfect assumption because there's some problems there, and that introduces some error. But so if we say, okay, the signal is traveling at the speed of light, we measure the time delay, we multiply those two together. So speed is in length per unit time. We multiply that by time cancels out, and we get distance, we get the length. So another illustration of that, here is our satellite, here's our GPS receiver here, and the satellite and the receiver clock are at 0 milliseconds, and the signal travels to the receiver, and when the receiver gets it, we're at 67.3 milliseconds. And so that is the time that it took the signal to make it to the receiver. That's our travel time here. We multiply that by the speed of the light, and we get our distance to our satellite. So we can see that measuring this travel time very accurately is extremely important, because we're going to be using that then to calculate our position. And so what they have to do then is put atomic clocks into the satellite so that they have an accuracy of time measurement on the order of nanoseconds. That's billionths of a second, 10 to the minus 9. These are expensive clocks, and of course we can't put an atomic clock in our receiver, but what happens is our receiver can adjust its quartz clock to match the atomic clock. So your GPS receiver actually keeps very, very accurate time because it's adjusting its clock to match the atomic clock on the satellite. So just a quick review. From the time lag in the signal from the 4 satellites, the GPS receiver computes the range, or the distance, from the receiver to the satellite. And then, using the distance to those 4 satellites, it can trilaterate to determine its position. And that's what's going on in a GPS receiver. So I mentioned that we have another problem, and that is that the speed of light is constant in a vacuum, but those signals have to travel through the Earth's atmosphere. And when those electromagnetic signals travel through the Earth's atmosphere, it affects the speed of the signal. And that can introduce some error into the position that's calculated by our GPS receiver. And in a couple weeks, we'll talk about atmospheric errors, and we'll talk about what we can do to correct them, which ones we can remove, and how we can do that. So the distance to the satellite is calculated by the time lag in the signal. But the other piece of information is that we need to know where the satellite is. So think about our seismometer example with the earthquakes. We know where the seismometer is located, so we know the earthquake is on some circle, some radius from it, right? But we have to know where the seismometer is. So in this case, the satellite is like the seismometer. So our GPS receiver needs to know where the satellite is. And that information is included in the navigation message. That extra data that's modulated on the carrier wave includes information about where the satellites are. The bummer is that the satellite orbits aren't perfect, and they do vary a little bit. You have gravitational pull of the moon and sun and other celestial bodies that can affect the orbit. And the monitoring stations are tracking those satellites to make sure that their orbits aren't varying too much. And if they need to be adjusted, the master control station can send a message to the satellite to adjust its orbit. And so that can be taken care of. But in order to know exactly where the satellites are, we need that navigation message, that extra bit of data. So just to sort of wrap this up, what happens is our GPS receiver picks up transmissions of signals from at least 4 satellites. It measures the time delay in the signal transmission. It uses that time delay to compute the distance to the satellite from the GPS receiver, assuming that the signal is traveling at the speed of light. And then it combines those distance measurements with the information from the navigation message, which includes the precise location of each satellite, to trilaterate to determine the receiver's position, which is recorded in the GPS unit as latitude, longitude, and elevation. So that sort of summarizes what we have going on with a GPS receiver calculating your position.